Today is the day to learn something new. You learn something new every day if you pay attention. Good afternoon to one and all. On behalf of Department of Electronics and Communication Engineering in M.P.NACHIMUTHU M.JAGANATHAN Engineering College, we extend a warm and hearty welcome to one and all gathered here for the webinar on National Technology Day. First, I welcome Ms.A.Mythili from final year ECE to welcome the gathering.
An affable noon to everyone gathered today for the it is not late for very much. First, I would to welcome our beloved response for a ceremony, Dr. Vasanta Sudhandan ma'am, who is
I welcome you. Then I would to extend my warm welcome to today's chief guest, Dr.V.Rajeshkumar Associate Professor, Year University Vellore. I welcome you, sir.
Then thank you, Mythili.
Okay, sir. Then I would like to welcome our respected principal, M. Ramesh sir, who has made his kind presence on this great occasion. I welcome you, sir. And I would like to welcome our department HOD, Dr. G.Rubashree. I welcome you, sir. I welcome all of various department HODs, teaching and non-teaching staff members of our college. I welcome you all. Finally, I welcome our students, friends for our college. Once again, I welcome you all. Thank you.
Thank you, Mythili. A true educator is the one who knows the way, goes the way, and shows the way. It is my pleasure to invite our HOD, Dr. G. Ravikumar sir, who constantly motivates and guides us to facilitate the gathering.
Thank you, Ms. So, I'm Dr. G. Ravikumar, head of the Department of ECE. So, first of all, I thank to our correspondent madam to organizing this event and conducting this event a successful one. And also, I welcome the resource person, Dr.V.Rajeshkumar, ASP, ECE, VIT Vellore. First of all, thanks to the resource person. He is going to given a wonderful seminar to our students. First of all, thank you. The main aim of this program is we are going to celebrate the National Technology Day. So how the day is organized, when the day is organized, everybody may be knowing about that. So in 1998, a paramount incident is occurred in our country. That is done by our former Prime Minister Vajpayee done it. So what is that incident? Everyone knowing it. A series of explosion is done in Pokhran. So on the day is May 11, 1998. So from 1999 May 11th onwards, so we are celebrating that day as a National Technology Day. So from that day onwards, we are celebrating as a National Technology Day. So today, this year, our Union Minister Deventhiran declared the theme as integrated approach in science and technology for a sustainable future. Today this year, this is the topic for celebrating the National Technology Day. So, this is the viewer. So I hand out to the session our resource person, Dr. V.Rajeshkumar. Okay, sir. Thank you for everyone.
Thank you, sir. The beautiful thing about learning is that so no one can take it away from you. Now I request Ms.P.Bavatharani from 3rd year ECE to introduce the chief guest. Good afternoon to everyone gathered here today virtually for this webinar on National Technology Day. Before years that are easy or cheap, those only worth having which comes as the result of our fighting. I am extremely privileged to have the opportunity to introduce the chief guest, Dr. V. Rajeshkumar, Associate Professor of ECE, VIT University in Vellore. He was completed his bachelor degree of Electronics and Communication Engineering, M.P.NACHIMUTHU M.JAGANATHAN Engineering College in ERODE, Master degree in Sona College of Technology, Salem, Doctor of Philosophy, National Institute of Technology in Tiruchirappalli, and Research Supervisor in NIT Tiruchirappalli. He published several journals and he attended many conferences in national and international levels. Our guest professional experience as follows. He worked as the assistant professor, Karpagan Institute of Technology, Coimbatore. He worked as a research scholar in Shivagasi. And the present is worked as a associate professor, grade 1 in VIT University Vellore. He has done various projects like implementation of microstrip array antenna for Wi-Fi MAX-based transceiver system post-graduation, implementation of beam forming algorithm for smart base station antenna for mobile communication under graduation, automation in public distribution system in mini project, scholastic achievements, Board of Studies member for Annapurna Engineering College, Salem, recognized as supervisor under Anna University, Chennai, Board of Studies members for Sona College of Technology, Salem, received fellowship from MHRD pursuing PhD at National Institute of Technology, Richmond. Presented a paper on the topic of wireless battery charging system using RF energy and won the second prize in 25th South East Asia Regional Computer Confederation of Computer Society of India. Presented a paper on the topic of water as a fuel and won the first prize in national level Tech Fest held at the SRM University. Won first prize the Dexterous Manager contest conducted by Anna University, Chennai. Appreciated and awarded special prize for the project of automation in distribution system for by ERODE district. Secured second rank in Bachelors of Engineering during the academic year 2007. Secured second rank in Master of Engineering during the academic year 2010 to 2011. Secured school first mark in both SSLC and HSLC. Of the top achievers, I know they are the life learners, looking for new skills, insights, and ideas. If they are not learning, they are not. Now I conclude my introduction speech about our chief guest. Thank you for everyone for this wonderful opportunity. Thank you all. Thank you, Bavathan. The difference between successful people and really successful people is that really successful people say no to almost everything. Next, I hand over the session to the chief guest, Dr. V. Rajeshkumar, Associate Professor, ECE, Grade 1, VIT University, Vellore. I welcome you, sir.
So thank you, Nithyshree and Rubashree, for your wonderful introduction. So with this, let me go into our session directly, and then we can have a discussion at the end. Let me share my screen. So is my screen visible and am I audible to you?
Yes, Rajesh. Yes.
Yes, thank you, sir. Yes. Okay. Thank you for giving a wonderful opportunity to discuss about my expertise on National Technological Day. So today I'm going to deliver a lecture on recent advancement in antennas and its application. So coming to this point, I could understand there are many students who are yet to start their research or the project work in the field of antennas, or some of the faculty members may be already working in the field of antennas and applications. So it is always better to begin with some basics and then move with the advanced topics. So in that aspect, I will just proceed with some of the fundamentals of antennas and followed by the various applications and advancements in this particular domain. So fine. So this is my agenda. So I'm going to start with antenna fundamentals and followed by linear transmission lines which are required to feed the antennas, and then microstrip antenna design, the fundamental. Then types of planar antennas, followed by RF and microwave and millimeter waves, which is one of the technological advancement that we can see nowadays, that is millimeter waves. It is especially utilized for 5G communications. And then fabrication and the practical constraints that you may face while you are manufacturing an antenna, followed by opportunity and conclusion. This is the agenda for the day. So let me begin with some of the fundamentals. So these fundamentals, the students, those who are in the third year might be started going through this particular introduction, the aerial, or you can call it as a radiator. So, or I can say it is kind of a transducer that converts an alternating current into radio frequency field and vice versa. Hopefully, you will be studying two important subjects. Going through these two important subjects, you may get into it called antennas. So, antenna, you know, that is very important element in wireless communication. Okay. For example, you can this, and then your antenna is going to transmit a signal over the free space. So here comes the important aspect. Okay, you know, in electromagnetic field theory also, you are studying something is how the field is going to be radiated in going wire element from the transmission line to free space. So that release both your wire element as well as your free space. So there comes an important thing over here with the antenna. So now you can see it is a kind of an interface between transmitter and receiver. So one antenna is going to transmit the signal, whereas the other antenna is going to receive the signal which are transmitted by the. Okay, so I can say that as a impedance transformer. Way I'm telling this particular point, it is called as impedance transformer means it converts, it modifies the 377 transmission line usually designed for a 50. Expecting the 677. So these are one key point that you need to remember. That is why the antennas are sometimes referred to be impedance. Rajesh, the voice is breaking. So now, looking at this, you have a transmitting antenna, you have a receiving antenna. So this is what happens inside the transmission line. If you are supplying with an alternating signal like this, okay, so it's going to keep on changing from positive cycle to negative cycle. So the transition will be like this. So when it is, the transmission line is slightly flat. Okay, generally it is a guided wave inside the transmission. What you see, it is a guided wave, and it is going to operate in the TEM mode, transverse electromagnetic mode. And when you are slowly flaring it, okay, what happens since the field also keep on changing. So finally, it will form a wave which is called plane waves. From the guided wave to plane wave, this transition is happening in the antennas. So that's why this region is to be transition region. Whereas when you come to the free space, your waves are converted to plane waves. And the plane waves again are received by the receiving antenna, and further conversions are being done. This is what generally happens in an antenna system. So now we can say like this: we have several personal computers, cables, okay, and other electronic equipments. They also emit radiation. So can we classify them as antennas? For example, if you have a piece of wire, that wire also may emit some kind of radiation. So whether can we classify them as antenna means? The actual answer is no, because always in antennas we use the far field radiation. Okay, always the radiation which are transmitted over a long distance are going to be useful. They are going to carry the signal that to the large distance. So that signal, the far field signal, we are going to consider for our transmission and reception. So what this piece is, the cables or some of the electronic equipment, they emit some kind of radiation, no? And these are referred to be near. So the near fields, we are not going to completely use, but some of the applications they use near fields also. Okay. How you are defining far fields? You would have studied in your theory that when the transmitting system, when the transmitting distance is much greater than the lambda. Lambda is referring to the size of the antenna. With respect to the size of the antenna, how much wavelength? Okay, lambda is generally wavelength. So you can convert the antenna size into in terms of wavelength. How much lambda the size of the antenna is going to be, that we can convert, and compared to that, if the distance that the wave travels is going to be much higher means, then you can classify them as a far fields. So then near fields are really not useful, or whether they can be used for some of the application means, definitely they can be used for some of the applications. So some of the applications that are mentioned here, you can see, for example, transformer. In electrical engineering, this is the core concept over there. The transformer couples from primary to secondary coil. Okay, you have a primary coil and you have a secondary coil. So how the energy is coupled through primary to secondary, that is because of the near field coupling. Okay, near field coupling. Coming to the electronics, we have something called wireless chargers. So in the wireless chargers, if you keep your mobile phone over the device, it will get charged. So how it is getting charged? It is through the wireless, like near field energy, near field coupling. Otherwise, we can call it as near field coupling. And circuit breakers and in some of the capacitors, RFID applications. Okay, RFID applications are all, you are pausing and receiving the signal, which is very close to the element. So it is going to be near field. The field that you are transmitting and receiving are going to be the near fields. What may be a planar transmission line? Any idea? Okay, you have a PCB board. Okay, you have a PCB board. Okay, in the PCB board, suppose the antenna is made like this. Yeah, patch antenna is made like this. For example, you are using a mobile phone. The mobile phone is going to have a PCB board like this. Inside you have various components. Okay, various electronic components you have inside your mobile phone. Okay, there definitely there will be a PCB board. So in that PCB board, your antenna is actually something like this. It may be a patch antenna or planar inverted wave antenna, whatever it may be. So for that antenna, so actually what is the role of this coaxial line, the other telephone cables? So they carry the signal from one point to another point. Either you can classify them into two ways. One is for power transfer, to carry the signal from power from one point to another point, or the signal from one point to another point. The coaxial or the conventional transmission lines are used. So coming to the planar transmission line. So if you have an antenna like this, this antenna has to be given with the input. So that input you can give through a transmission line called planar transmission line. So what is a planar transmission line means? You have a PCB board. Over a PCB board, some of the conductor areas, the conductor copper area is etched like this. Okay, a small line of width and thickness. You can have width of 2 mm, a length of 7 mm, something like this. So this line, this particular planar line is referred to be transmission line. And through this, the antenna may be connected further in your PCB boards. So everything on a planar structure. It's a kind of a paper. On the planar surface, you are going to have your transmission line as well as antenna. So this is referred to the planar transmission line. So for understanding the planar transmission line or the working of an antenna, we need to get one important aspect from your transmission line. That is about return loss. Have you studied about return loss somewhere? Return loss or reflection coefficient? Return loss or reflection coefficient. So whenever you start your research in antenna engineering, okay, since many of you are the B.Tech students over there, maybe when you are choosing a final year project, you should have a clear understanding of some of the fundamentals related to antenna engineering. So very first and important parameters, wherever I go, I will tell about this particular point, because this is one of the key things that you need to remember when you are studying about antenna engineering. So this is the key word that relates your transmission line theory and your antenna theory. Both are related to this particular parameter called reflection coefficient. Reflection coefficient. Okay. In transmission line theory, you studied about a transmission line of impedance Z0, which is referred to be the characteristic impedance, which is constant over the length of the line. Am I correct? You studied something like this, no? Any third year or final year students? Can you say yes or no? There will be a transmission line, and the transmission line will have a characteristic impedance called Z0, and there will be a, then definitely this transmission line going to be connected with a load, and you can refer the load impedance as ZL. Okay. Then line, this is line impedance, this is load impedance. Then we define one parameter called tau, which is equal to ZL minus Z0 divided by ZL plus Z0. So have we come across this expression? So just give me an acknowledgement, just yes or no. Hello? Are I audible?
Rajesh, yes, you are audible, Rajesh.
Okay, okay. Thank you, Mukesh. Thank you. Okay. Don't be worried that I'm going to teach like other like normal class lectures. That's very important thing that I wanted to convey, because the students, when you are starting your research in the field of antenna, you understand this expression. Only then you'll be able to get how an antenna radiates, at what frequency radiates, how they are defining. So these key points lies in this expression. Maybe when you are studying transmission line theory, you just like that you come across this expression, but you should know the fundamentals of this particular expression. So that from the transmission line theory, you can still little expand the expression, reflected power to incident power, and when you substitute your reflected signal, incident signal. So don't worry about this expression. Final expression you may have like this: minus 10 log tau square or minus 20 log tau EV. So this expression is a return loss expression, where you have one parameter called tau. So this tau defines a reflection coefficient. I already mentioned a reflection coefficient, and this can be written as ZL minus Z0 divided by ZL plus Z0. So what are ZL and Z0 means? Your Z0 is the characteristic impedance of the line. ZL is the load impedance of the line. So general basic, the fundamental of a transmission line theory is, whenever your ZL and your Z0, these two impedance, whenever your Z0 and ZL are perfectly matched, so the maximum power transfer is going to happen with your antenna. Your antenna is going to transmit all the signal which is going to receive through the transmission. Okay, when the condition is ZL must be equal to Z0. Okay, suppose if your ZL is not equal to Z0, okay, your characteristic impedance is something like 50 ohm and your load impedance something like 75 ohm or 80 ohm, by the situation, your antenna is not going to radiate all the energy which is going to receive by through the transmission line. So that point of time, what happens? A part of the signal is going to be transmitted like this, and part of the signal will reflect back towards the transmission line. So this signal is said to be a reflected signal. Then the transmitted signal and reflected signal together forms a kind of a wave pattern in your transmission line that is referred to be standing waves. Okay, this is referred to be standing waves. Okay, and then you will call something called standing wave ratio also. Okay, so these concepts we have studied in your transmission line. So how it is going to be used in antenna engineering means, look at this expression. Now ZL equal to Z0. Consider the first condition. ZL equal to Z0, that load impedance and the characteristic impedance of the antenna are perfectly matched. Characteristic impedance of the transmission line and the antenna impedance. ZL may be your antenna impedance. Both are perfectly matched. Means your tau will become ZL minus Z0. So you're obviously 0. Your tau will become 0. So tau is 0 when your transmission line and antenna impedance are perfectly matched. So when putting tau equal to 0 here, tau equal to 0, if you substitute, you will get your return loss equal to minus infinity. So this is one conclusion. So I wanted to write one conclusion. I will write here. When ZL equal to Z0, this is the first case, ZL equal to Z0, and you will arrive a condition called tau equal to 0. That says your return loss must be equal to minus infinity. So now I'll come to the second condition. When ZL not matched with Z0, okay, then there will be a reflection. There will be a reflection. Definitely this will have some coefficient, and this value will be ranging from 0 to 1. Okay, 1 means complete reflection. Now you assume ZL and Z0 not at all matched, and you have a complete reflection. Whatever you are transmitting through the transmission line, your load is not at all taking anything. Everything it is transmitted back to the transmission line. So now you take tau equal to 1. So what tau equal to 1 indicates? It's a complete reflection from the antenna. So in this case, what you will get by return loss equal to minus 20 log 2. So in this expression, when you put tau equal to 1, when you substitute tau equal to 1, you will get 0 dB, because logarithmic of 1 will become 0 dB. So I will be getting return loss equal to 0 dB. So this is the phenomena, this is the fundamental concept utilized in antenna engineering to check that designed antenna is working at which frequency. That particular thing is being measured through this return loss plot. So whenever now you come to this particular graph. Okay, now I have designed an antenna. It is a kind of a rectangular patch antenna. I have designed a patch antenna like this. Okay, this is your antenna. This is your transmission line. And how this antenna, once you design with a certain length and width means, then you assume application is going to be a WLAN or Wi-Fi application. You are designing an antenna for Wi-Fi application. The Wi-Fi application is going to have the frequency range of 2.4 GHz. 2.4 GHz is the Wi-Fi application. So you made all the calculation, you designed your antenna through any simulation software, and then you are going to test it. So for testing it, we require an element called vector network analyzer, VNA. So every antenna, once it is designed through a software, then it has to be fabricated through the printed technology, PCB technology. Then it has to be connected. This transmission will be connected to a coaxial connector, and then it will be connected to a vector network analyzer. You would have seen many spectrum analyzers, a kind of CRO. What you basically, if I want to tell in a simple way, it is like a CRO. So you have a coaxial probe connected to the CRO, right, through your circuit board. Similar to that, here the circuit board will be your antenna. Your antenna will be connected through a coaxial cable, and it will be connected to the VNA, that is vector network analyzer. Then your vector network analyzer is giving a plot like this. Okay, then as a designer, you should conclude, okay, I was designing an antenna for my Wi-Fi application, whether my antenna is working efficiently at that particular frequency or it is not working in that frequency. That you have to conclude by looking at a plot which is generated through this VNA. Now VNA, you assume now my VNA is giving a plot like this. Okay, my VNA is giving a plot like this. So now, can anyone say at what frequency my antenna is working based on this plot? Any one student, just tell me what this may be indicating. This is dBS11, otherwise you can write this as a return loss. Okay, this is the return loss plot. So okay, now from this graph value I'll come to now. I'll explain you. Now you assume x-axis is plotted for 0 to 5 GHz. This we can take frequency in terms of GHz. So 0 to 5 GHz I have taken. I am getting a plot like this. Now you have to conclude at what frequency my antenna is working, at what frequency it is not at all working. So now based on these two conditions, first of all you see return loss equal to 0 dB. So this is 0, 5, minus 5 dB, 10 dB like that. This is in dB scale. Okay. Now this is 0 dB. Now return loss equal to 0 dB. I am getting over the frequency range from, for example, 0.2 like 0.2 GHz to around 1 or 2 GHz, exactly around 2 GHz. Till this range, I have 0 dB. I have 0 dB. Then what this indicates? Tau equal to 1 means complete reflection. Return loss equal to 0 dB. I'm getting that you can observe from the graph. So this what indicates means from 0 to 2 GHz, my antenna is not at all radiating anything. It is 0 dB. That indicates complete reflection. So your transmission line is connected to the antenna like this. The signal which is transmitted, everything is reflected back during these frequency ranges. Okay. Again here, somewhere here it is close to 0 dB. Again here slow 0 dB. So these are the frequencies where your antenna is not at all working. Then you come here suddenly for a point 2.4 GHz. This is 2.4 GHz. Exactly at 2.4 GHz, I'm getting around minus 35 dB. Even though it is not infinity, okay, infinity means it's perfect matching condition. There should not be any reflection at all. But basically, we will not be able to design an antenna which will give a perfect matching condition. Okay. So considering that, now tau may not be 0, but maybe some lesser value, 0.2, 0.1, like that, very 10% reflection. 0.1 means 10%, 1 means 100% reflection. So 0.1 or 0.2 means 20% reflection. Remaining 80% is transmitted efficiently at that particular frequency. So I'm getting return loss value minus 35 dB around 2.5 GHz means, okay, then this says my antenna is working exactly at 2.4 GHz. This is the plot usually you will get when you are connecting your antenna to a vector network analyzer. So this is what you will be doing during the testing process. Okay, during the testing process. So 2.54 GHz is my antenna frequency. Okay, minus 35 dB is there, minus 10 dB here you can see minus 10 dB is there. So can you conclude what is the optimum level for an antenna to radiate and receive? Okay, because there are industrial standards, we have our mobile phones and all. So up to what return loss is sufficient for radiating and receiving the signal means minus 10 dB is the threshold point. Minus 10 dB. So minus 10 dB means it indirectly says 90%. So this is the threshold point. So minus 10 dB is the threshold level for an antenna to transmit and receive. So what you can observe here, dual bands. So this is said to be dual band. The antenna is working at dual band. One is at 2.4 GHz, other one is at around 3.6 GHz. 3.6 GHz. So at these frequencies, 2.4 and 3.6, your antenna will be able to transmit and receive the signal efficiently. But other frequencies, the reflection is close to 100%. So nothing is transmitted by the antenna. So this is how you have to relate the transmission line theory with the antenna. So now what you studied with the transmission line theory, now it is related to the antenna. When it is connected to the antenna, how your reflection parameter tau is being utilized to measure, to analyze whether your antenna is working or not. To understand that, to conclude that your tau, your reflection coefficient phenomena is being utilized in antenna engineering. So okay, this is how you can relate your transmission line engineering with the antenna. Okay. So coming to the types of transmission lines, we have non-planar. You know that coaxial, two-wire, waveguides. Waveguide also like you have a circular waveguide, rectangular waveguide. So waveguide also a kind of transmission line because they also do the same process. They transmit the energy from one point to another, or they transmit the signal from one point to another. Usually waveguides are utilized for high power applications as well as for high frequency applications. Can you give any example where you are using waveguides? Okay, the best example is radar applications, and many of us started using microwave oven, right? Microwave oven. So inside the microwave oven, the fundamental component is waveguide. Okay, anyhow, the microwave signal at 2.4 GHz has to be generated. Once the signal is generated with the help of a magnetron, that will be carried through a waveguide. That will be carried through a waveguide. So there, the waveguide is a common element. These are non-planar transmission. Coming to the planar transmission line, again we have certain classifications. Okay, what I have explained, the PCB board, you have an antenna. Then to feed the antenna, we have a transmission line. That transmission line is referred to a planar transmission line. That can be classified into something like microstrip, strip line, slot line, coplanar waveguide, coplanar line. These are some of the classifications. I'll just show you how these lines will look like. Okay, yeah. So why the advantage of planar transmission line? We know that is a very, so PCB boards you are able to see These are very small boards. Within that small boards, you know the dimension of the antenna. You are using mobile phones with some 6-inch or 4-inch length. So within that, you have a PCB board which comprises of all your signal processing unit, all your speakers, battery. Okay. So there you see the antenna size. It is very, very minimum. With that area, your transmission line also is going to occupy very smaller area. So always we are going to use for gigahertz frequencies the antenna size, and as well as your transmission lines are going to be in the millimeter range. Okay, they are going to be in the millimeter range. So some of the examples of this transmission lines and then feeding technologies. So this figure you can see. This one is known as microstrip line. So what is microstrip line means? Your PCB board is something like this. In the top of the PCB board, if you have a transmission line, it is said to be microstrip. So what is strip line means? Inside it's like a sandwiched one. Inside the substrate, you will have the strip line. And you have something called parallel line, coplanar waveguide, coplanar strip line. These are some of the classifications of the planar transmission line. Then coming to the feeding methods. So this for the beginners. Okay, suppose you are going to start your research in the field of antenna engineering. So then you should know what are the feeding methods are available, what kind of method you should select for before you are proceeding into your antenna fabrication. So this I will give us some overview of feeding methods. May be useful when you are designing an antenna through software. So coming to the feeding methods, you can see microstrip feed. This is the conventional feed, I can say. So almost over a decade, over 4 or 5 decades, they are using this kind of feed lines, microstrip feed lines. This is the conventional thing. What you see here, something like this, your antenna. Okay, so this is your antenna. So this is your feed line. So this feed line is referred to be microstrip feed. And then there is a small change to this line, and it is said to be microstrip insert feed. So why this feed has come, I will tell you. And we have microstrip matched feed. So otherwise it is known as quarter wave transformer feed. Okay, quarter wave transformer feed. So this is a specific feed line utilized for impedance matching process. I will explain that. And then there is something called coaxial feed or probe feed. And these two are less utilized feeding mechanism in antenna engineering, aperture coupled to proximity coupled, because this makes your antenna design so complex. So most commonly used transmission lines are these, and then coplanar waveguide feed. So I'll just show you a pictorial representation how these feed lines will look like. This is your microstrip antenna. This is your microstrip feed line. Okay, when it is connected something like this will deliver the power to the antenna, and the antenna will go for the radiation, and now will radiate the energy over the free space. Okay, this is what happened in the microstrip feed. So microstrip feed is nothing but a metal strip directly attached to your antenna. This is said to be microstrip feed. Microstrip insert feed. So why they move to your insert feed? Okay, when you are referring maybe the research papers, and some of the papers they will be using this kind of microstrip antenna, and some of the papers they will be using this kind of feeding technology. You would have wondered why they are using these two lines. What may be the indication? What may be the implication because of that? Okay, what is the advantage of this feed line? So it is very simple. Usually an antenna will look like this. Okay, at the end, okay, both the end of the antenna. Okay, this is one end, this is another end of the antenna. So at the ends of the antenna is look like an open circuit. Okay, it is like just an open circuit. Usually in open circuit, the voltage will be it's like an open circuit. You can see, you know, the fundamental expression is equal to V by I. Okay, is equal to V by I. So this is open circuit. Obviously, your voltage will be maximum and your current will be minimum in the open circuits. So current will be minimum. So when the current is minimum, okay, when I is minimum, okay, when you look at the impedance at the surfaces, at the edges of the antenna, when you look at the impedance Z, I is minimum means Z will be larger. Z will be larger. Z means is nothing, impedance of the antenna at the surfaces. It will be very, very higher. So when you are connecting a transmission line which is of 50 ohm impedance, most probably we will be using a 50 ohm transmission line. When you are connecting a 50 ohm transmission line to a patch antenna like this, what happens is, yeah, you are connecting a low impedance line to a high impedance surface. Obviously, that will lead to, maybe you may assume 150 ohm. So two impedances are highly mismatched, and when you are connecting to that, the reflections will be more. As I explained earlier, the reflections are more means maybe your antenna has to resonate like this, Instead of this, your return loss will be very, very minimum. The matching will be poor and majority of the signal will reflect back. So to overcome that, when you are moving inside, the current will go maximum. The current will be maximum when you are moving inside the patch antenna. Okay, because here voltage is maximum. When you look at the exact center, current will be maximum, voltage will be minimum when you are moving over the patch antenna. Okay, that because of that concept, if you are moving somewhat inside, your impedance of the surface here maybe 150 ohm means when you are moving inside, it may slightly reduce to 50 ohm also at certain point. So you need to identify that particular point. There are certain formulas are available in the Barathan textbook for identifying the depth, how much distance we need to go inside. So this process makes your antenna impedance comfortable for matching. So maybe 50 ohm matching will be possible to get here. So this is referred to be microstrip inset feed. Okay, microstrip inset feed. And there comes matched feed. Okay, so here what concept? You would have studied about stub matching. So the second year students maybe in the transition line you would have studied about stub matching. So you will be going for the stub matching when the load impedance ZL is complex. R plus JX. ZL equal to R plus JX. When your load impedance is complex, then you will be using a procedure called single stub matching, double stub matching, and as well as LC matching. So these three matching process you will be using when your load impedance is complex. Okay, note this part. Suppose the load impedance is real, your ZL equal to purely real. I write here. ZL equal to something called R ohm, so 50 ohm, 60 ohm, like a purely real. So by that time we will be using a quarter wave transformer line. What is quarter wave transformer line means? The impedance of this quarter wave section must be equal to, you are having a transfer line which is having impedance of 50 ohm, and you have an antenna which is having impedance of 60 ohm. Obviously this 50 ohm and 60 ohm both are not matched. To match two real impedances, the quarter wave section can be used. What is quarter wave section means? The length of the transmission line is lambda by 4. The line length is going to be lambda by 4. So what is the outcome of this? Then how we are going to give the matching for these two lines means very simple. If you are designing this quarter wave section of particular impedance, that impedance must be equal to the square root of two impedances, 50 into 60. So definitely 300, and if you take the square root of this, that will give certain impedance. If you give that impedance to this quarter wave section, then this will be perfectly matched. So this is how the microstrip matched feed or quarter wave transformer feed is being utilized in engineering. So you may wonder many cases when you read various research papers, you will see why this paper they are using this kind of feed, why they use this kind of feed, and somewhere you can observe quarter wave transformer feed. So this is a fundamental difference. This is the reason they went for this kind of matching procedures. The next one is coaxial feed. It is very simple feeding mechanism. If you have a patch antenna like this, anywhere on the patch, no need of connecting the transfer line at the edge anywhere. You have a PCB board means directly you can make a drill at some point. Okay, it's like a wire, and directly you can make the coaxial cables inner conductor. Okay, inner conductor may touch this copper portion. So by this process, this will radiate. This will get the required signal to transmit. Okay, this kind of process is said to be coaxial feed or pro feed. And then comes aperture coupled feed. Aperture coupled feed means your feed line will be at the bottom, antenna element will be top. In between there will be a slot. This slot will couple the energy through the coupling process. This is aperture coupled feed. This proximity coupled feed, and these two are very rarely used. You can go through later. Not that much importance they are having. So next one is coplanar waveguide. Coplanar waveguide, what advantage they have here means other transmission lines. What you see, you have a transmitting element at the top, ground at the bottom. The ground at the bottom. You can see the ground layer is at the bottom. Even you can see the patch antenna. This is the patch element. The bottom you see one black color thick line is there. No, that is said to be ground. So this is with the conventional antenna. And when you come to the CPW antenna, coplanar waveguide antenna, your ground layer also present in the top of the patch. Bottom layer is completely free. So this is referred to be single-sided PCB. So the manufacturing wise, it is more easier compared to the other PCB antennas, and cost wise is very less, and as well as production wise is very easy, and packaging wise is going to be very, very easy. Okay, you have the ground also the top layers, so packaging also will be much easier for this coplanar wavelet. Okay, this is another kind of feeding mechanism. Okay, coming to the microstrip antenna, we have certain advantage. We know that is modern day technology. We use wireless gadgets of very smaller size. So these wireless gadgets definitely you see Wi-Fi adapters. These are all very small. So you see the antenna which is replaced in the Wi-Fi adapter also is going to be very small. So the microstrip antenna, what advantage we have is they are very simple, portable with any kind of devices and smaller in size, lightweight. These are all some basic advantages we have with the microstrip antennas. Without the antenna, we don't have any technology to use. Okay, everything you see, mobile phones, you have Bluetooth headphones nowadays. So everything we have some kind of wireless transmission. So they require some kind of device to transmit and receive. So some of the examples are mentioned here. You can see to it that the planar antennas are utilized in many applications. And these are all some of the examples. The practical fabricated antenna. This is coaxial connector. This will be connected to coaxial cable and it will be connected to the VNA for testing purposes. This is the radiating element. Okay, some examples are given. And various shapes of the microstrip antennas also available. Okay, this can look good. Okay, coming to the wireless communication system. So modern day technology, as the technology demands, we need to upgrade our antenna design technique as well. Okay, earlier we have used only for one frequency called 2.4 GHz. Okay, but nowadays we use 2.4 GHz for your Wi-Fi and conventionally used 1.8 GHz GSM applications. Okay, nowadays LTE has come, 4G has come, now 5G has come. So technology upgradation is keep on taking place. For example, initially we used only 2.4 GHz for Wi-Fi application. That is otherwise supposed to be ISM band. What is ISM band means? Industrial, scientific, medical. Make a note, industry, scientific and medical. Research purpose, industry purpose, medical purpose. This is a unlicensed band. So any research that can be carried out in this frequency can be executed and can be tested. This is unlicensed band, and so this band is utilized for many of the applications. Later on, what happens? More technology development have been taken place, and because of that, this become overcrowded. So they developed another standard called 802.11 pp as well as 11A. And application to this 2.4 GHz, they utilized another band, 5.15 GHz to 5.35 GHz. If you, when you are purchasing a mobile phone, if you see the specifications, they will mention about these standards. Have anyone seen this? What band it uses? It uses for the Wi-Fi applications. It will be mentioned definitely when you go to Flipkart or Amazon. When you are looking at the mobile specification before you purchase, it will clearly indicate. They will clearly indicate what kind of frequency they are using for your cellular communication. What are the frequency channels it supports, and as well as what is the frequency it supports for Wi-Fi application, whether 2.4 GHz band or 5.15 GHz, 802.11A or P by G. These standards definitely are mentioned. Have anyone seen this? So fine. So like this, you can make a note of these frequency bands. The beginners, you may start your research in these frequencies because these are the commercial applications. So Wi-Fi and WLAN, WiMAX, these are the commercial applications. So you can start your research in these frequencies. Then you can move to the frequency called 5G communication or frequencies of 4G applications or the frequencies of GSM application. Like that, you can switch over your research, upgrade your research to the second level. First level, you start with the fundamental frequency which are used for the commercial applications. Okay, this is the one example I wanted to say. So coming to the antenna design requirements. So towards the beginners, I wanted to specify everybody, those who start your research in antenna field, you may start with the patch antenna. Because the patch antenna, we have set of formulas to calculate this length, width of the antenna. Okay, width and length of the antenna can be estimated through set of equations. Okay, well-developed equations are available to design up. For example, you want 2.4 GHz. Easily, you can design the antenna for 2.4 GHz with the help of the equations. Equivalent transmission line also can be easily designed for that. Okay, my aim is to now design an antenna for 4.5 GHz. I don't want a patch antenna. then what you can do, the thing is very simple. You can apply any modern day technology. We have various technologies, electronic band gap structures, EBG, and defected ground structures, DGS, fractal structures. One example I kept, that is a fractal structure, is very easy for you to understand. That's why I kept the fractal structure here. Okay, and some more slots, many things are there. So how to modify the fundamental antenna towards an application means very simple. You have to have the aim, like you may require to design an antenna for multi-frequency or multifunctional purpose, and radiating pattern you wanted to have at the desired direction. So for achieving all to this, you are going to perform any of this particular operation. Okay, you are going to perform any of this operation. So by doing this, you will be able to achieve the required antenna. Okay, modifying the main radiator. What is main radiator in the patch means? This is your main radiator. Modifying the ground plane, which is at the bottom of your patch. This is your patch means the bottom of the microstrip is going to have patch ground line. The ground plane you can have introduce some slot or metamaterial structures. Okay, and modifying the substrate. What is substrate? It's not mentioned. I hope you understand. The PCB board I was mentioning, right? So that board is referred to be substrate. That substrate only is going to hold your antenna. You are going to, through the etching process, you are going to make conductor portion of that particular length and width. Okay, then modifying the substrate characteristics, one of the methodology we can have towards designing an antenna. And the modification may involve incorporation of some slits, slots, patches with multiple radiating elements, more than one stack to patches, multiple branches. Multiple branches are there means it may lead to multiple frequencies also. So that I will explain with the design example called a fractal antenna. So challenges for the antenna engineers nowadays, you need to look at the bandwidth for the particular application, how much bandwidth is required. Okay, bandwidth for the particular application, how much bandwidth it requires, gain of the antenna, and then polarization, isolation, beamwidth, and all we require. Nowadays, every in addition to the wireless gadgets, every house is going to have an antenna. It is nothing but your DTH antenna, your parabolic dish. Everybody have come across one antenna. Every house is going to have hold one antenna for the television purpose. That is your DTH antenna. These are all coming under high gain antenna. High gain antenna. Why it is I am telling high gain antenna? So they are going to communicate with the satellites. Okay, they are going to receive the signal over the satellite. So that's why they are referred to be high gain antennas, DTH antennas. So we need to look at the gain also. According to the design requirements, we need to proceed towards the antenna design process. Mechanical wise, you may have a limitation in the size and integration with other circuits, how it's going to be possible. Okay, that characteristics also we need to consider when you are designing an antenna. And commercialization wise, mass production is possible or not, and the cost, whether it is going to involve very less cost or high cost. So these things has to be checked. So these are some challenges that are going to be there in the antenna engineering. So types of planar antennas, we have many. I just go with one example called fractal antennas. So fractal is a term introduced by a mathematician. What is fractal means? You may see a Christmas tree, or you may see something like a triangular structure like this. So what you see here is said to be Sierpinski fractal structure. Sierpinski fractal structure. So what you see here is a Sierpinski fractal structure. What you see, if you take any portion of this antenna, for example, if you take this particular portion, this will resemble the entire structure of your antenna. Or else if you take this smaller portion, any smaller portion will indicate or refer to the original structure. Okay, this is said to be self-similar. If you take every portion, it is repeating the whole structure. This is said to be self-similar. Okay, and something called space filling also available. So this one antenna, I'll just give an example to you. So why we need to go for this? When I have a design like this, okay, this is resonating at 2.4 GHz. Why I need to go for an antenna which is a radiating element? Why I am modifying like this? You can see with this example. Suppose my antenna design requires 4 bands. Okay, my antenna design like this, it may require multiple bands like this. Okay, then for multiple bands, if I'm going with multiple antennas, okay, inside my wireless gadget, I'm installing one antenna for this frequency, one antenna for this frequency, another antenna for this frequency. Means cost wise, it's going to be very high, and area wise, it is going to occupy majority of your area in your device. and it is very difficult to accommodate multiple antennas inside the structure. So these situations, you can go with only one antenna, but that antenna should produce all these frequencies. That is said to be multiband antenna. So what you see here, these are the wavelengths. Maybe the electrical length of this structure is much higher, so it may produce a frequency much lower frequency. You know, one basic parameter, lambda equal to C by F. C by F. Okay. If frequency increases, your lambda decreases. Okay. At lower frequencies, lambda will be higher. At low frequency, lambda will be higher. What you can see here, you can see the signal itself. The lambda is going to be much higher. The wavelength of the signal is much higher. Compared to the smaller area, lambda is smaller. Here, lambda is much smaller. So, lambda is smaller means obviously it indicates going to generate high frequencies. So, inside a single antenna structure, when we have a multiple element, okay, like this, multiple element like this, multiple smaller areas like this. So, each edges will start to radiate. This edge will radiate, this edge will radiate, signal will pass through this, signal will pass through this, like that. What may happen? Finally, you may get multiple bands as an outcome. So with the help of a single antenna, you are capable to generate multiple frequencies. This is referred to be multiband antenna. Okay, you are achieving 5 different frequencies in one antenna. This is one example, just I wanted to say, it's a fractal antenna. By modifying the structure, how you are able to get multiple frequency from a single antenna. Okay, this is said to be multi-resonant characteristics. Each frequency, it is satisfying the norms of the antenna design. Okay. So some of the fractal structures are given here as an example. Okay, coming to the development, technological development in the technology day, National Technology Day, we have to discuss what technological development is going through this and engineering. For example, we started with 1G, later on moved to 2G systems, then 3G systems. Nowadays we are utilizing 4G. So very near, we are going to utilize the features of 5G technology. Okay, 5G technology. So what advantage we have with the 5G technology? So between the 2022, 2030, definitely this is going to be implemented. So it is very easy for building communication and much faster way, and well as the bandwidth that is going to offer. It's going to be enormously high. You cannot imagine. So that multiple GB of videos may be downloaded with a fraction of second time, as well as the uploading time may be reduced, as well as how that technology is going to connect various things we can see here. So entertainment applications, you may have a car-to-car communication, the driverless vehicle communication is getting established, and connected houses through Wi-Fi. So everything is possible with the 5G technology. So going to 5G, okay, at lower frequencies, we know the lambda is going to be much larger at lower frequencies. Then what may be utilized for 5G? So one of the research that nowadays is getting progressed in the area of millimeter wave communication. What you can see here, millimeter wave communication. So why it is called as millimeter wave? If you calculate the lambda for that frequency, lambda will be in the millimeter range. For example, if you take 30 gigahertz, it is going to be 10 mm. Okay, lambda equal to C by F, you all know. Okay. If you calculate for 3 gigahertz, maybe 10 centimeter you will get lambda. So there are centimeter ranges. And when you go for millimeter, for example, the range starts with 30 gigahertz. For 30 gigahertz, you will get lambda as mm. And for 300 gigahertz, you will get 1 mm. So the lambda ranges from 1 millimeter to 10 millimeter. So the lambda is in the range of millimeter, and these frequencies from 30 gigahertz to 300 gigahertz, these frequencies are referred to be millimeter waves. So the 5G applications, the research have been started in the frequency of millimeter waves. So why we need to go for millimeter waves when there is existence of microwaves? Obviously, you see, like the frequency reuse can be done enormously, as well as the spectrum. We have the spectrum availability in this frequency, 30 to 300 gigahertz. If you see, we have more spectrum available for transmission and reception. Also, their wavelengths are much smaller. So the frequency reuse within the small range, you can make effective communication, and frequency reuse can be done effectively, because when the wavelength is much smaller, the signal will fade away after a certain distance. So then how to overcome this process? Because in microwaves, we use cell phone towers for 10 kilometer range or 5 kilometer range like that. When you go for millimeter wave frequencies, we need to have mini towers at different places. Okay, and coming to the frequency range, this you can note down the few researchers, like few researchers have been started in these frequencies, 22 to 29 gigahertz, 76 to 77 gigahertz, and 59 to 64 gigahertz. So these are the frequency bands are being utilized in millimeter wave applications. Okay, these are the frequencies. Currently, the researchers started working and they started developing antenna in these frequency ranges, which are suitable for 5G communications. Okay, 5G communications. Are you fine with this? Then there is a limitation in 5G. What is the limitation that we have means packaging is very difficult because the antenna size we are going to use is going to be much lesser. Okay, much lesser. And then manufacturing wise, since we are going to use it millimeter waves, we need greater precision hardware to develop the millimeter wave antennas. And we know this point very clearly. At the high frequencies, the attenuation loss is going to be much higher. So it can be hardly used for long distance. So as I said, we need to utilize for short distance and maybe house-to-house communication or kind of a Wi-Fi technology you can use for short distance, and later it can be developed to longer distance communication. And fabrication. So this is one of the final point I wanted to convey. So when the people started working in antenna field, first of all, before starting the simulation, because in simulation you are having complete freedom to select any substrate to simulate, but when go for a fabrication, maybe that substrate may not be available. So you have to check with the market what kind of substrate is available, maybe FR4, RT2-RIDE. So what is available and what thickness of the substrate is available, what is the last engine. This decides the last component of the substrate. So these things has to be identified first before getting into fabrication, and fabrication facilities and availability of connectors and measuring equipment. Nowadays, the problem is we started working in 24 GHz for millimeter wave application, but many places we don't have the measurement facility for this 24 GHz application. So you can go with only simulations. This is one drawback we have with the millimeter wave communications. So these are some of the practical constraints we have with the antenna design. Okay, thank you. What you see is an anechoic chamber. So there the antenna can be tested. Just a sample is shown here, where the horn antenna is being placed, and your test antenna will be kept here, and it can be tested inside the anechoic chamber. So with this, I would like to conclude my session. Now it is open to you all. If you have any queries, we can discuss. We can interact actually. In between, I asked 2 questions, but I did not get the response from your side. But now you can feel free and you can discuss. If you have any doubts, let's proceed with that. So whether you are got some new point today, the students, because many of you going to start your research or B.Tech final year project coming months. I believe the third year students, it may be useful when you are starting your research in antennas. Can I get some response? Nithyshree?
Thank you, sir. Thank you for taking. Thank you, sir. Thank you for taking your time to share your knowledge with us. Things work out best for those who make the best of how things work out. Now, I would like to call upon Ms.G.Rubashree from second year ECE department to propose the vote of thanks.
An affable note to everyone for this webinar on National Technology Week. It gives an immense pleasure to deliver the vote of thanks for this event with all the dignitaries this year. I would like to thank our chief guest who honored this webinar with such inspirational thoughts. Thank you, sir. I would like to thank our beloved sir. Thank you, sir. I would like to thank our department lecturer, Dr.V.Rajeshkumar sir. Thank you, sir. I would like to thank our various department lecturers, teaching and non-teaching staff members of our college. I thank you all. Finally, I thank all the students and friends of our college. And again, I thank one and all. Thank you all.
Thank you,
Thank you,
Rubashree.
Rubashree.
And just a minute, I would like to thank this wonderful opportunity given to me, Maheswaran sir. And I would like to thank our HOD sir, Ravikumar sir, for giving this wonderful opportunity. Also, I would like to thank my teachers, Anita ma'am, Mohan sir is there. And it's a wonderful feeling for me because as a proud alumni of MP and MJ Engineering Institution, So today I have presented to you. So I completed my B.Tech in 2005 to 2009 from MP and M.J Engineering College, and after that I have got, even though we are at some rural place, we have got sufficient knowledge over there, and it takes me to NIT, and now I'm working at VIT Vellore. So all the credits goes to my MP and faculty members, and thank you all. I would like to thank our correspondent ma'am, Sudhanathan ma'am, for giving wonderful opportunity. Thank you, ma'am.
Thank you, Raj.
Thank you, sir. Thank you, Mahesh.
Thank you. Hello, students. Okay.
Deventhiran.
Rajesh, I saw you later, sir. Thank you so much.
Mahesh, thank you, Mahesh. Okay, I'll leave now. Yeah.
Okay, thank you. Okay, Raj. Thank you.
Rajesh, thank you. Rajesh, thank you so much.
Thank you, Ra.
Take care, ma. I வீட்ல எல்லாம் கேட்டதா சொல்லுங்க, ma. Take care.
Okay, na.
ரொம்ப கோல்டா இருக்கும் போல, பயங்கர கோல்டு நினைக்கிறேன்.
ஆமா, நான் நேத்து ஆக்சுவலா ஊருக்கு வரதுனால கோல்ட் ஆயிடுச்சு ஆக்சுவலா.
டிராவல்ல வந்ததுல இதா இருக்கும்னு நினைக்கிறேன்.
ஆமா, நேத்து கொஞ்சம் ரெய்னியா இருந்துச்சு, வரும்போது அப்படியே கோல்ட் ஆயிடுச்சு.
செஷன் சூப்பரா இருந்துச்சுமா. நல்லா பேசிக்கா ஒவ்வொரு ஸ்டெப்பா எல்லாம் சொல்லி கொடுத்துருக்காமா பசங்களுக்கு.
தேங்க்ஸ்ண்ணா.
கண்டிப்பா ரீச் ஆயிருக்கும். அவங்க கேள்வி கேட்க ஆஸ் யூஷுவல் பயப்படுவாங்க இல்லையா?
பரவாயில்ல மகேஷ். அதான் பிசிக்கலா ஒரு நாள் வர வந்து ஒரு நல்ல இன்சைட்.
ஆமா ராஜேஷ். அதனால
கண்டிப்பா
வரல, பார்க்கலாம், இன்டராக்ட் பண்றேன் ஸ்டூடண்ட்ஸோட வந்து.
வெல்கம் வாங்க. கண்டிப்பா
ஒரு நாள் டேட் ஃபிக்ஸ் பண்ணி சொல்லுங்க.
ஓகே,
கண்டிப்பா நம்ம பண்ணலாம். நம்ம
நேர்ல ஒரு சின்ன ஹேண்ட்ஸ் ஆன் மாதிரி வச்சோம்னா ஸ்டூடண்ட் ப்ராஜெக்ட் பண்ண போகும்போது மேபி அவங்களுக்கு யூஸ்ஃபுல்லா இருக்கும். சிமுலேஷன் வெர்ஷன்ஸ் வச்சு அவங்க ஏதாவது ட்ரை பண்ணலாம். கண்டிப்பா வருவாங்க.
ஓகே ராஜேஷ். ஓகே,
கண்டிப்பா கம்யூனிகேஷன் ரிலேட்டடா ஆண்டனா ரிலேட்டடா பண்ணோம்னா ஈஸியா இருக்கும் கொஞ்சம்.
கண்டிப்பா.
ஓகே
ராஜேஷ். தேங்க் யூ. டேக் கேர்.
தேங்க்ஸ்.
பை.
ஓகே.
இந்த பக்கம்